Hello and welcome to today's video. In this video, we are going to talk about orthogonal projections. You will remember that we have introduced a scalar product, that we have introduced orthogonality, meaning scalar product of two vectors is 0, and based on that, we have discussed orthogonal complements of linear spaces. In the next step that we discuss in this video, we will decompose any given vector with respect to a given subspace. So if we have a linear subspace U, we decompose a vector in the surrounding vector space V into a part that is in U and a part that is in U orthogonal to U. And these two parts will be called the orthogonal projections of a vector to the vector spaces U and U ortho. So in this video, we're going to be concerned with this definition and of course also with the computation of such orthogonal projections. So the section is called orthogonal projection. I'll start you off with the definition. As usual, we have a Euclidean vector space, so vector space equipped with a scalar product. So let's say let V be a Euclidean vector space. And as always, just think of R to the n. And U is a subspace of that. A linear subspace. Of V with orthogonal complement U ortho. For a vector V in the vector space, we already know there is a decomposition of V into two parts, one in U, one in the orthogonal complement. So for a vector V in capital V, let U be in capital U, U ortho be in capital U ortho, and let those be the unique vectors with V equals U plus U ortho. And in this definition, we just give names to those vectors. U is then called the orthogonal projection of V on the vector space capital U. And it will usually be denoted as U equals the projection of V onto U, like this. Furthermore, this projection, of course, defines a mapping from V into U. And this is also referred to as the orthogonal projection on U. And it's denoted as projection of U. That's a mapping from V to U, that assigns to each V in V its orthogonal projection on U. This mapping is also called the orthogonal projection on U. Now, let's see in a quick sketch what is happening here. Let's say we are in the two-dimensional space R2. Like this. We have a vector. So let this be our vector V. And then, of course, we need U and U ortho, two vector spaces. To make things easy for now, we just take this axis here as U, and then this axis here is the orthogonal complement. Then what are the projections of V on U and on U ortho? For the orthogonal projection on U, what we do is we decompose V into a vector in U and a vector that is perpendicular to U. So what we need to do is basically find this point here, and this vector here is then the part of V that is in U or parallel to U. So this here is the vector U, which is the projection of V onto U. While this here this vector here, that is then the projection of V onto U ortho. So that is U ortho. Okay, so what we have here is V is decomposed into U plus U ortho. One is in U, one is in U ortho, and those are the projections on the respective spaces. Now, of course, we'd like to know how we can compute such an orthogonal projection, and that's going to be something that we'll investigate now. So the question is, how do we obtain an orthogonal projection? Let's say we have a space U, subset of R to the n. We work in R to the n for now. And let's say we have a basis. So that is described by a basis U1 to UK, a basis of U. For the moment, we'll take any basis. It doesn't have to be an ONB or something like this. And also, let's say we have a vector V that is in R to the n, and we want to find its orthogonal projection. So we want to find U in U, U ortho in U ortho, with V equals U plus U ortho. How do we do this? Well, to make things a little easier, a little more concise, let's take this basis U1 to UK and write this into a matrix. We'll write this as columns of a matrix. So let's say A be the matrix that contains these U's as their columns. So that's the matrix with columns U1 to UK. So that describes the space U if you want. Right? So U is then the column space of A. So now we'd like to find a vector in U and a vector in U ortho that have the given properties here. What does that mean exactly? So we need to find U in this column space of A and U ortho in U ortho with V equals U plus U ortho. So the column space is described as the number of linear combinations of the columns of A. So what we can also do is we can try to find the right coefficients to get this vector U. Okay, so U is a linear combination of U1 to UK, and that means we can also find coefficients. We call those x1 to xk, and we'll write them in a vector x. So that's a vector in R to the k with U equals x1 times U1 plus x2 times U2 and so on up to xk times uk. And that is the same thing as A times x, right? Remember, multiplying a vector to the right of a matrix is equal to taking a linear combination of the columns. So AX represents our vector U. And that means the task is to find these x values. So find x in R to the k such that the following hold. Two conditions. The first condition is A times x, remember that is U, plus that vector U ortho is equal to V. And second, U ortho needs to be in the right space, in the orthogonal complement to U. That means it needs to be orthogonal to the space U, and that means it needs to be orthogonal to all the basis vectors of that space. So the basis vectors are the columns of A. That means the scalar product of each column of A and U ortho needs to be 0. So the scalar product of Ui and U ortho needs to be 0 for all I in K. Now we can write this a little more concisely. Let's copy the first equation here first. Second one, we can write this with the help of A, the matrix A, by saying, well, these scalar products, those can be expressed as the rows of a transposed, right? The columns of A are those U1 to UK, so the rows of a transposed are also those U1 to UK. And we multiply those with our vector U ortho. Then what happens here is each row of that result here is a scalar product between a row of A transpose and U ortho. So this is the vector that has in its rows exactly the scalar products that we want. and we want that to be 0. Right? So we have those two equations, and now we can start reformulating things a little. So the first equation that can be solved for U ortho, of course. And then U ortho is V minus AX. And just copy the second one for now. A transpose U ortho is 0. And then we can take the U ortho from the first equation and just substitute it into the second one. So we get U ortho equals V minus AX, and the second is then A transposed V minus AX is the 0 vector. Or in other words, we can simplify that a little. First one stays as it is. Sorry. The second one becomes A transposed AX equals A transposed V. So here we have a matrix. Remember, A has n rows and k columns, right? So that means this matrix here, that is a matrix in R k by k. That X is a vector in Rk, so this is a linear equation in X that we can solve. This is a fixed value. This is a matrix, also fixed, so we can solve this equation. And once we solve this equation for X, we can then compute U ortho, of course. So that is what we're going to do. Step 1, we're going to solve this equation here. ATAX equals ATV. And step 2, we're going to set U equal AX, and then U ortho equal to V minus AX. And that's the decomposition that we want. So by solving this equation, we'll get the correct result. The only question that remains is, can this equation be solved, and is the solution unique? And that's the thing that we still have to show. So remaining question is, can this equation be solved? And is that solution unique? And to prove that this is the case, what we'll have to do is we have to prove that the rank of this matrix here, of A transpose A, that this is K. So this matrix has full rank, at least under certain conditions. And the one condition that we'll assume here is about A, sorry. We know that A is composed of bases in its K columns. So that means the matrix A has rank K. We know that. And then the question is, can we infer that A transpose A then has rank K as well? That's what we're going to prove right now. So we will show that the rank of A transpose A is K, and thus ATAX equals ATV has a unique solution. And actually that's not that hard to prove. What we're going to do is we're going to show that the kernel of A transpose A is the same as the kernel of A. We will do this by showing kernel of ATA is equal to kernel of A. That implies the following. So, you know, the rank of A transpose A is related to the kernel of A transpose A by the rank nullity theorem. A transpose A has k columns. So the rank is k minus the dimension of the kernel of A transpose A. And now if that kernel is the same as that of A, then we have k minus the dimension of the kernel of A. Now, again, using rank nullity, we know that the dimension of a kernel of A is the same as the number of columns of A minus the rank of A. A has k columns, so we have k minus rank of A. And finally, we know the rank of A because A has k linearly independent columns, because those columns form bases, remember? That means the rank is k. So we get k minus k here. And what remains is just k. And that proves that the rank is, in fact, k. So what's left to do is show that the kernel is actually the same. So to show the kernel of ATA is equal to the kernel of A, first consider an element in the kernel of A transpose A. So let X be such an element. Then that means, by definition, A transpose A times X is the zero vector. That's the definition of being in the kernel. And that in turn means that X transposed, I can multiply that on the left of that whole equation, right? Because we have a k by k matrix, X is a k vector, so that is defined. So I can just multiply that on the left, and that is then X transposed times the zero vector, which is of course 0, the number 0. So what do we have here? What we have here is AX and X transposed A transposed. Now, by the rules of transposition and matrix multiplication, that's the same thing as AX transposed AX. So that is 0. Well, that is the same thing as the norm of AX squared. So that's 0. And by the rules of norms, that would mean the norm is 0 if and only if the vector inside the norm is 0. So this is the 0 vector. And that in turn means that X solves the equation AX equals 0. So X is in the kernel of A. That was the first part of what we have to prove here. So an element that is in the kernel of ATA is also in the kernel of A. And vice versa, so the second case, let X be in the kernel of A. Well, that's the easier case. Then that means AX equals the 0 vector. So that means A transposed times AX is the same thing as A transposed times the 0 vector, and that is of course 0. So that means X is also in the kernel of ATA. So we have shown that these two kernels actually agree, and that means the rank of our matrix ATA is in fact K, so we can uniquely solve that system of linear equations. So the way to find, or one possible way to find such a orthogonal projection is to first compute a solution of this equation system here, and then just set u to AX and u ortho to v minus ax. And there we have it. Okay, so a very special case of that, and a very common case, is if u, the vector space u, is given by a orthonormal basis. And in that case, things get even simpler. So let's have a quick look at a theorem that details this. Let's say we have a Euclidean vector space. Let V be a Euclidean vector space. Let U be in V a linear subspace. And let's say we have U1 to UK, and that is an orthonormal basis of U. Then we can compute the projection of any vector on U even easier, because the following holds. Then for any V in capital V, we have the following. The first is basically what we know already. If we define the matrix A as consisting of the columns U1, U2, and so on up to UK, we then get the projection of V on U is, remember, that is the same thing as first solving the system A transposed A equals ATV. So what is that solution? Well, A transposed A has full rank, has rank K, and is quadratic, so it can be inverted. So that solution is A transposed A to the -1 times ATV. And that gives us a vector x of coefficients. So to get the actual vector u, the projection, we have to multiply A with that result here. So A times this here would be the projection. That's true for the general case. Now in this special case, where we have an orthonormal basis in the columns of A, what is A transposed A? Well, actually, each entry in A transposed A is a scalar product of a row of A transposed and a column of A. So each entry is a scalar product of Ui and Uj. Right? So that matrix here. Each entry is of the form Ui, Uj. And as this is an orthonormal base, this means all these entries are 0 with the exception of Ui, Ui. So when you make the same vector with itself, then the result is 1. So what this really is this is the identity matrix. So we can just leave that out. And that means the result is really A times A transposed V. So that becomes really easy. Part 2, we can also express this a little differently and in a way that is probably easier for most computational purposes. If we look at what happens here, this A transposed V, remember A transposed, the rows of A transposed are the vectors U1 to UK. So this A transposed V here, this actually consists of the scalar products of the U's and V. like this. So the first row is the scalar product of u1 and v, and so on. The last row is the scalar product of uk and v. And what happens then is this vector here is multiplied with a. Now the columns of a are the u's again. So this factor here is multiplied by u1, the second is multiplied by u2, and so on. This is multiplied by uk. So what you really get here is a sum of these scalar products times the respective basis vectors. And that's the formula that we write in part 2 here. That's also a way to express a projection. So the projection of v onto u can also be written as the scalar product of u1 and v times u1 plus the scalar product of u2 and v times u2, and so on, up to the scalar product of uk and v times uk. And that is what we use most often, actually. So this is a projection of a vector v in onto u once you have an orthonormal basis of u. So that's the important thing here. This formula, this general formula, that holds anytime. You can use that for any basis you want. This here only holds if the u's u1 to uk form an orthonormal basis. So you first need an orthonormal basis, and then you can compute projections in this way. Okay? So that's the important point to keep in mind here. And finally, we consider one very special case. Let's say u is spanned by just one vector, we call it y. Then of course an orthonormal base of u is easy to be found. So the vector y divided by its norm is an ONB of u. Well, what happens then? What about the projection then? So the projection of v on u is then simply given by projection of v on u. If we look at this last formula here, we only have one of these summands. So what we have to do here basically is just compute the scalar product of y over the norm of y and v, and then multiply this by y over the norm of y. Right? So this is a projection, or you can also express this as saying we have the scalar product of y and v over the norm of y squared times y. So this is a projection of a vector onto the line spanned by the vector y here. Right? Projection of v onto the line span y. That's the case of just one vector. So if we have a normalized y, we can say the scalar product. What does that actually mean? The scalar product is something like the length of the projection of v onto y. So that's an interpretation of the scalar product. So yv if y is normalized, so if the norm is 1, then this scalar product yv can be interpreted as the length, or rather the signed length, of the projection of V onto the line spanned by Y. So the scalar product kind of gives you the length of a projection, and that's a geometrical interpretation of that scalar product. Now, we'll have a closer look at that interpretation in one of the following videos to define general angles. But first, of course, one of the questions that is still open is, we said in this theorem here, we'd rather apply this formula, but to do this, we first need an orthonormal basis of U. So the open question is, how do we get an orthonormal basis of any given vector space? And that question will be answered in one of the upcoming videos. And as usual, I'll see you then.